Hey everybody, this is Mr. Ainsworth, and in this video, in section 2 here, we're going to talk about what's called the golden ratio and its connection with the Fibonacci numbers that we talked about in the previous lesson, and also extend it to what's called the golden rectangle. It's going to be pretty cool. You're going to need a calculator to calculate some ratios here, so get out a scientific calculator here and get ready to start. The first thing we're going to do is we're going to write down the Fibonacci sequence that we all know and love and that we're familiar with in the last lesson. So it starts off with the two seeds, 1 and 1, and in the Fibonacci sequence, you add the two preceding numbers to get to the next one. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 and 8 is 13, 8 and 13, 21, 13 and 21, 34. These are the Fibonacci numbers. 21 and 54 is 55. All right, and then 34 and 55, 89. And then we get 134 plus 14, 144, and so on. These are the Fibonacci numbers here. First Fibonacci, so F1. Remember, I'm just doing a little recall. This is F1, this is F2, the second Fibonacci, this is the third Fibonacci, the fourth Fibonacci number, the fifth, F6 is 8, F7, the seventh one here is 13, and so on. Okay, so we're going to take these numbers here and calculate some ratios. We want all decimals to the nearest thousandths, okay, 3 decimal places. And then so you got to look at the fourth digit around the third. All right, so here we go. Let's get started. Get your calculator nearby so you're going to be able to calculate. So F2 divided by F1. So we'll go 1 divided by 1. This is a tough one. 1 divided by 1. I know you don't need a calculator for that, do you? Okay, and we get 1, of course, right? And then we take the 2 divided by 1, this third Fibonacci number, which is 2, divided by 1, and that's just 2. I'm going to calculate a bunch of ratios here. So, and then F4 is 3, and then 3 divided by 2. So 3 divided by 2, that's 1.5. We don't need a calculator there. And then we take 5 divided by 3, which is 1 2/3 or 1.6 bar. So 1.667, or you can say 1.6 bar because it repeats. And use your calculator whenever you need it. Take the sixth one divided by the fifth one. 8 divided by 5. That's 1 3/5. That's 1.060. I know those by heart. And then you take 13 divided by 8. All right, that's 1 5/8. I think it's 1.625, but let's double check. So 13 divided by 8. It's 1.625. 1.625. And then 21 divided by 13. The Fibonacci's are right here in the second column here. And that's, what does that equal to? Okay, so like I said, just use your calculator and get some ratios. So 1.615. 1.615. Oh, look, these numbers are getting closer. So it's 1, then 2, then 1.5, then 1.667, 1.60, 1.625, 1. They're very, very close. They're all agreeing to the second digit, or the what's called the tens place. Then you take 34 divided by 21. This is where technology helps out a little bit. 34 divided by 21, you get 1.619. 1.619. And then you take 55 divided by 34. 55 divided by 34, and you get 1.618. 1.618. Then you take 89 divided by 55. And then you take 89 divided by 55. Just keep going for it, and you get 1.61818. So 1.618 again. So now they're agreeing to the third place right here. All right, so it's pretty obvious that if you keep on going here, and we could keep on going if we had more time, that the pattern of the ratios here, as n increases to infinity here, as n, all right, increases to infinity, this is the infinity symbol, what's called the lemniscate, as n gets bigger and bigger and bigger, super large, like F100 divided by F99, all right, we're talking about the ratio Fn to, F sub n minus 1, the one before it, approaches a very, very special number, 1.618, so on. But what is that number? What does it mean? What is its significance? Where do we see it in nature? And things of that nature. Okay, well, one place that we do see it is when we solve this quadratic equation. And when we have x squared equals x plus 1, this comes in play some places, so I wanted to show it to you, and let's solve it. Okay, and it becomes a very, very special number here. So let's set this equal to 0. So we're going to subtract x and subtract 1. So we got x squared is equal to x plus 1. Got to subtract x here and subtract 1. So subtract x, subtract 1. And if you just read it, x squared minus x minus 1, x squared minus x minus 1 is equal to 0. Why? Because, well, that's 0 and that's 0. So what are the coefficients here? Well, a is 1, b is negative 1, and c is negative 1. So a is 1, b is negative 1, c is negative 1. And I'm going to substitute this in the quadratic formula here. I'm going to put the quad formula up here where I have some room. Quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. You guys already know that. So what do we get as a solution here? We get the opposite of negative 1 plus or minus the square root of negative 1 squared minus 4 times a, which is 1, times c, negative 1, all divided by 2 times a, which is 1. Well, what do we get? We get 1 plus or minus the square root of 1. I'd say negative 1 squared is 1, and then I see a double negative here. 4 times 1 is 4, times 1 is 4. So I see 1 plus 4 in there, 1 plus 4, all divided by, well, 2 times 1 is usually 2. So I get 1 plus or minus the square root of 5, all divided by 2. Well, this gives me two solutions, obviously. So x is equal to 1 plus the root 5 divided by 2. It also gives me 1 minus the root 5, root 5, all divided by 2. Now, what are these values, okay? So let's figure this out. Let's use your calculator here, and we're going to put parentheses around the numerator because we're going to take all of the numerator divided by 2, and then same thing with the second solution here, and check out their decimal equivalents. Okay, so let's use your calculator again. Let's bring it up and let's clear it out so we can start fresh. And let's take the quantity, use left parentheses, 1 plus the square root of 5. All right, get out of the root sign, right parentheses, divide that by 2 and hit enter. And notice, oh my gosh, look at that number. We've seen that in the ratio table, or the table of ratios, before, so 1.618. So x is equal to 1.618 here, so on. And then what is the second one? Let's see here. Let's recall the entry back. I'm going to go back to the plus sign and change it to a minus sign. If you don't know or have this calculator or have this feature, don't worry about it. Just type it in again, and you get negative 0.618. So negative 0.618. All right, we call this the golden ratio, okay? So this I'm talking about right here. Let me highlight it. Not this one, but this one here. This right here is called the golden ratio, and we've seen it before in Benet's formula, and we also see it in the table of ratios here. When you take consecutive Fibonacci numbers and divide them, any term divided by the term before it, approaches what's called the golden ratio. So this right here, it's approximately 1.618, but the exact golden ratio is 1 plus root 5 over 2. Okay, called the golden ratio. All right, and golden ratio, very, very special number, and we see it all over mathematics. We see it in nature, all over the places you're going to see, and we also see it in art and architecture. It's called the golden ratio. Okay, the exact form, let me just be very specific here, is 1 plus the square root of 5 divided by 2, and its approximation that I want you to memorize is 1.618. Okay, let me highlight this. All right, and where have we seen it? Let's answer this question again. I said it was Benet's formula, but let me just state it again. Where have we seen it? Benet's formula to find the nth Fibonacci number. All right. It's used to find the nth Fibonacci number. Used to find the nth Fibonacci number. Okay, and you can go back to our previous lesson to recall that formula there. All right, now this golden ratio is seen in many different places and is called phi. Okay, and what we're going to do is we're going to play around with it here. So turn on the next page here. This golden ratio, which we call phi, let's highlight that, has a very, very special name, phi, with a Latin symbol or a Greek symbol, phi. Okay, that's the Greek symbol there. All right, and it's 1 plus root 5 all divided by 2. It's also known as the divine proportion, the golden number, the golden section, and so on. And if you're with me in class here, I'd probably show a video here to show all kinds of relationships and places where you see this special number in art, architecture, and nature. You can also Google that if you like and take a look at it on your own. It's so many different places and so well studied, it's phenomenal. All right, but what we want to do right now is we want to take a look at powers of the golden ratio, phi to the nth power. All right, that's how you say it, phi, all right, to the nth power. All right, what happens, all right, what happens to phi when you raise it to a power? All right, so what we're going to do is this. We're going to take a look at powers, starting with the third power and then the fourth power of phi. We know that phi, as before, is 1 plus root 5 over 2. It came from the solution of that quadratic, all right, that we just solved, all right, x squared plus x plus 1, or excuse me, x squared equals x plus 1. And because of x is the solution of that, x is the same thing as phi. And because of that, I say x is equal to phi now, okay? There's phi. Just, actually, it's, well, we'll just say phi here. And that phi, if you replace x with phi, you got phi squared equals phi plus 1. Because of that, we can play with the powers of phi. All right, here we go. So phi cubed, you have to understand what phi cubed is. Phi cubed can be rewritten as phi times phi squared. Okay, we know that x times x squared equals x cubed. Same thing here. Phi times phi squared is phi cubed. No big deal. Now we understand that phi squared is just phi equals 1. So I'm going to make a little substitution here that where we have phi, all right, and then I'm going to substitute what phi squared is equal to. It's phi plus 1. So phi plus 1 here. There's a little substitution. Look here and here. They're equal. And then if I distribute through, I get phi times phi, which is phi squared, all right, plus phi. Oops, not q, but phi. Sorry. All right, so we got phi squared plus phi, and you got to say, okay, no big deal. All right, but let's just play with this here and just kind of go along here because I'm going to keep on doing this. We're going to develop a pattern so we can recognize something. Okay, so bear with me here. I can see that phi's in common. Excuse me, I can see that we have phi squared again here, and then because of phi squared, I have phi squared. I know that every time I see it, it's just phi plus 1. So what I'm going to do is I'm going to substitute in phi plus 1, again here, my second substitution here, all right, and then I have to add this phi. But what do we get? I get 2 phi, I got 2 of them, 2 phi's plus 1. So 2 times phi plus 1. So I substituted twice there and kind of just manipulating things. All right, and you're saying, oh, okay, where are we going on this? Well, in order to see that, we kind of have to do it again. All right, so let's do it again. So phi to the fourth is nothing more than phi times phi cubed. When you multiply variables, you add your exponents. All right, 1 plus 2 is 3, 1 plus 3 is 4, and so on. Okay. So what do I know? Well, I already developed phi cubed, so I'm going to take my previous result, 2 times phi plus 1, and substitute it in. So I got phi here, and then I'm going to make a substitution. I know that phi cubed is 2 phi plus 1. So 2 phi plus 1. Okay, you say Ainsworth, great. Okay, so what? So now what we're going to do is we're going to distribute twice. 2 times phi times 2 phi is 2 times phi squared, and then phi times 1 as well, that's just phi. You say, great. Okay, so what do we do? Well, we see another phi squared. So my second substitution would be right here. What phi squared is. I want to substitute in what it is, equal to. Every time I see a phi squared, I know it's phi plus 1. So what I want to do is substitute it in 2 times and then phi plus 1. There's my substitution right here and here. And then I'm going to add that remaining phi. But how many phis do we have? Well, we got to distribute, right? So I got 2 phi plus phi was 3 phi. And then 2 times 1 is 2, so I got plus 3 phi plus 2. And you're thinking, okay, great, this is great. I've got initially phi cubed is 2 phi plus 1, phi to the fourth is 3 phi plus 2. I mean, where are we going with all this? Well, in order to see that, we got to continue. So let's play the same game again. So we got phi times phi to the fourth. All right, well, I just developed phi to the fourth. I know it's 3 phi plus 2. So my first substitution is in for this one right here. I know that it's 3 phi plus 2. So I'm going to substitute that in. So I got phi times this value here, 3 phi plus 2. There's my substitution. Let me highlight it right there. In the previous step, I found that they're equal. And if you distribute through, like I did in the preceding steps, all right, I get 3 times phi squared plus 2 times phi. Okay, but once again, I got a phi squared, right? So anytime you see a phi squared, well, you got to substitute what it's equal to. So let's do that. So I've got 3 times whatever phi squared is right here, plus 2 phi. So I bring that phi squared in. I know that phi squared is phi plus 1. All right, and then I distribute again. I keep on repeating the process over and over again. So I get 3 phi plus 3 plus 2 phi. But 3 phi plus 2 phi is nothing more than 5 times phi, right? And then you got 3 times 1 is 3. Well, I'm looking at the coefficients here, 1 and 2 and 2 and 3 and 3 and 5. These numbers look kind of familiar because if you look at the Fibonacci sequence here, 1, 1, 2, 3, 5, 8, 13, and so on. If you look at the Fibonacci numbers, they're coming in here. They're hidden in these expressions. They're actually the coefficients. So if we knew how these numbers are related to the nth power, this is the power, then I'd be able to figure this out without doing this again. All right. Part of mathematics is looking at patterns and understanding how they come up. So what we're going to do is we're going to do that. But I need to do it one more time. Okay, so here we go. Phi to the sixth is phi times phi to the fifth. All right. When you multiply variables, you add exponents. Not q, it's supposed to be phi here. Okay, so phi to the fifth. There we go. 1 plus 5 is 6. So here we go. Now, I know phi to the fifth is 5 times phi plus 3. So my first substitution is just like the previous one. I need to substitute in right here what phi to the fifth is. Well, I know it's 5 phi plus 3. So 5 times phi plus 3. Now I need to distribute just like I did previously. So distribute twice. So here we go. 5 phi times phi is 5 phi squared plus 3 times phi. Well, anytime you see a phi squared, you got to substitute it what it's equal to. So here we go again. So we have 5 times whatever phi squared is plus 3 phi. Well, I know what phi squared is. It's up here. We keep on using it over and over again. It's phi plus 1. And distributing through, I get 5 phi plus 3 phi, which is 8 phi. And then 5 times 1 is 5. Look at the coefficients. 1, 2, 2, 3, 3, 5, 5, 8. Those are the Fibonacci numbers. Holy cow, look at that. Okay. Now, so what you have to do is understand what's going on here. there's a relationship between the nth power, okay, this is the nth power, okay, and the coefficients. Okay, there's a relationship there. So the coefficients of phi are actually the Fibonacci numbers. That's the observation about the coefficients, okay? The coefficients, okay, are Fibonacci numbers. That's the first thing you should notice here, are Fibonacci numbers. And if you understand that, then you could be able to write the powers of phi in respect to Fibonacci numbers. Now, what Fibonacci number is 8? That's what you have to understand. So let's see here. Let's put the Fibonacci numbers in the margin here. So F1 is 1, F2 is 1, F3 is 2, F4 is 3, F5 is 2 plus 3 is 5, F6 is equal to 8, F7 is equal to 5, and 8 is 13. Okay, so 8 here is the, oh my gosh, that's F6. And 5 here, that's F5. And this one, this is F5. And this is the fourth one. And right here, this is the fourth one. And this is the third one. Look at F3 is 2. And this is the second one. And this is, well, the first one. So F1. Excuse me, F3. This is F3, sorry. F3, and this is F2. So if you understand that these are just Fibonacci numbers, then you know the relationship between that and the power. So if we look at this and you compare, compare the power with the nth Fibonacci number, then there's a relationship there. So compare that with this. Let me see. Phi to the sixth power is the fifth or sixth Fibonacci number times phi plus the previous one. Phi to the fifth is the fifth Fibonacci number times phi plus the previous one. Phi to the fourth is the fourth Fibonacci number times phi plus the previous one. So I can say in general, phi to the nth power here is equal to the nth Fibonacci number, because notice that 6 corresponds to 6 here, is the nth Fibonacci number times phi plus the previous one, f sub n minus 1. Okay? And that's what you have to do. You can calculate any power of phi by understanding what just this basic idea right here, this formula here. Phi to the nth power is equal to the nth Fibonacci times phi plus the previous Fibonacci number. All right, and that's all there is to it. Okay, so let's kind of play around with the idea here. So on this one here, write all answers in terms of Fibonacci numbers and the golden ratio. Okay, so here we go. So this right here, that's the golden ratio. Got to remember that. The golden ratio, very, very special thing here. And so we got 8 times phi plus 5. So this is 8 times phi plus 5. Well, what is 8? Well, once again, let me bring those Fibonacci's over here so we can see them here. No. I'm going to do something really cool. Because I can. Oh, hang on. Let's try it again. No. Oh, yeah, there we go. Okay. All right, I'm going to bring them over here where I could use them again. Okay, so those are my Fibonacci numbers right there. So 8 is the sixth one. All right, so this is F6 times phi plus 5. 5 is the fifth one, the one preceding, right? So F's 5. Okay, remember that. It's always the nth Fibonacci times phi plus the one preceding it. Okay, this right here is just phi to the 12th. Phi to the 12th here, but what's that? Well, according to the formula, It's the 12th Fibonacci number times phi plus the one before it, which is f sub 11. Again, we're just playing around here. And in here, what do we have? This is Benet's formula. Ooh, this should look familiar. This is Benet's formula here for the nth Fibonacci number. So if notice that the exponent here, like the exponent of 7, that's n equals 7 right here. This corresponds to f7. All right, what is that? Well, that's 13. Okay, easy. On the fourth one here, we're going to find the value of a and b in each of the following equations. All right, so phi to the 10th, what is that? Well, let's go. Phi to the 10th, according to this, is the f 10, so or the 10th Fibonacci times phi plus the one before it, which is f9. Okay, so what is that? See, so 8, f8 is 21, f9, that's 34, f10 is 55. So f10 is 55. So this is equal to 55 times phi plus the one before it, 34. Okay, just develop the Fibonacci numbers again. All right, what is this guy? Let's see here. Phi to the 15th power. Okay, that's f15 times phi plus f14. Okay, you'd have to expand this, and when you do, all right, you get, if you keep on going here and get 5 more Fibonacci numbers here, you get 610 times phi plus the term before it, which is 377. Okay, you can calculate that on your own. All right, and that's how you play with it a little bit, okay? Powers of phi, powers of the golden ratio, which is 1 plus root 5 over 2. All right, I want you to now go ahead and try some homework problems that's in your book. All right, so do your best there. Do your homework, make yourself proud. All right, and I'll see you in my next lesson. And we're going to talk about facts of the Fibonacci sequence and the golden rectangle, and we're also going to go ahead and derive it and also construct it with a compass. Ooh, pretty cool. Okay, this is Mr. Ainsworth. I'll see you next time. Bye-bye.